Hi, I'm Domokos Kelen. I'm a PhD student here at SZTAKI, and I will talk about our collaboration with Ericsson about automated root cause analysis using explainable AI or asymmetric Shapley values. So first I will just give a general outline of the motivation of the problem, what we are trying to accomplish, and how we are trying to accomplish it. I will talk about the methods that we use, and then I will summarize two papers that we had in this research, a workshop paper and a conference paper. So the problem domain was something introduced to us by Ericsson. What they wanted to do is to find out the causes of performance degradation in their systems. So there's a large radio network, and we can measure the performance. Sometimes, for example, in download speed, sometimes the download speed is good. Actually, usually it's good, but sometimes it degrades, and we want to find out why the degradation happened. So the idea was to use explainable AI for this. What we can do is to collect a large amount of data of historic records of degradations happening, build a model to predict the degradations based on the observed features. They have hundreds of features that they can observe in the radio network. And then when the model accurately predicts that the degradation is going to happen, then we can use explainable AI to find out how the model predicted the degradation, and then we can assume that we can find the causes that were responsible for the degradation. So initially, we tried doing this using simply SHAP or Shapley additive explanations. It's a really popular method to do explainability nowadays. It can explain black box models, because the models that we use for predicting the performance are really complicated, like neural networks or gradient boosted decision trees, and we need these black box explanation methods to find something out about their inner workings, because they are too complicated to analyze by hand. So what SHAP does is it takes the model and compares an actual prediction to the average prediction. The average is the normal behavior, and when the degradation happens and the model predicts it, then we can divide the prediction into additive components based on different kinds of predictive features. So we can say that the behavior was degraded, and for example, the amount of load caused 1 megabyte of the degradation, and then the channel quality caused an additional 2 megabytes of degradation, etc. But there are some problems with SHAP. In general, SHAP is really hard to calculate. The naive way of calculating SHAP requires evaluating an exponential number of feature combinations, and there are a bunch of tricks or methods to evaluate SHAP for different models. There are general approaches, and there are separate approaches for neural networks and for decision trees. So a really large separation between two different kinds of Shapley values is how they handle correlated features. So let's say that we have some kind of redundancy in the data. We have two features that say pretty much the same thing about the target. And when we have hundreds of observations, this is to be expected. A bunch of features are going to be about the same thing, only with small differences. And if we explain a model, then we can expect the explanation to reflect the decisions made by the training of that model. So for example, if there are two very correlated or identical features, then the model is free to choose either of them to predict the target. And if we explain the model itself, then we can expect this arbitrary decision to be reflected in the explanations, which is not ideal. So this is called marginal SHAP, and the conditional SHAP is required to share the contribution between the two identical or very correlated features equally. in each case. And conditional SHAP is really hard to calculate. You have to, there are methods that build separate models for approximating distributions in the data to do this. The second problem we have is, and we need to do conditional Shapley values because we don't want arbitrary decisions to be reflected in the explanations that we do. The second problem is causality. When the problem happens in the system, it usually occurs in a single place and then propagates throughout the network. So it can be recognized from multiple different points in the measurements. So there are a bunch of features which reveal the problem to the model. And the most direct one is usually not the one that we are looking for. We are looking for the root cause where the problem originates, but the model tends to use the most direct connections to the target, which means the last feature in the causal chain. So the method that we use to avoid these problems, at least the causality one, is asymmetric Shapley values, which is responsible for handling the causal links between the variables. So this is not a way to discover causality. This is a way to use causality to improve the explanations. So we assume that domain experts have mapped out the possible connections between different variables. For example, load can influence interference, but interference cannot immediately influence load, so the causality is one direction. So asymmetric Shapley values is a general framework to include any kind of causal graph into the explanations, and then we can choose whether to emphasize the root causes or the immediate causes. And obviously we want to do the root causes because that's the general idea. So the first paper that we have in this research is a way to calculate asymmetric Shapley values in a way that the output reflects the conditional version of SHAP. So first, a few words about how asymmetric Shapley values works. What it does is it tries to predict the download speed in this example. And this calculation basically boils down to evaluating a number of expected values. So we try to see what the expected download speed would be given a certain set of predictive features. And then if we incrementally add the features in causal order, then the first point at which we can see the problem is the root cause. And the actual method is a bit more complicated than this because the causal order is not this well defined. We have to do a weighted average over a bunch of orderings. But this is the general idea. In this paper, we tested a number of methods to do this while staying with conditional Shapley values. And the most effective one was where we trained different models for these different expected values. And we do a small proof that this is supposed to approximate the conditional version of Shapley values. And fortunately, it can be calculated in practice because asymmetric Shapley values greatly reduces the number of evaluations that we have to do. We only have to do for the evaluations for starting subsets of the features. So we can train a number of models. In the end, I think we need to train something like 60 models in the practical scenario that we tried, which is a lot, but it's feasible. It just takes a long time. The second paper that we did in this topic is a theoretical analysis of the method itself, the asymmetric Shapley values method for root cause analysis. And we have discovered a problem in the algorithm itself. And so the problem is the following. If there is a connection between two features such that the problem is only visible when we can observe both features at the same time, then the asymmetric Shapley values algorithm determines the contributions incorrectly, because the first time that the problem becomes visible is when we include the second term, the second feature in the expected value, even though they are both responsible for the problem at the same time. And the blame will be placed on the second one, while it should be shared between the two. But this is really hard to even talk about in theory, because there is no ground truth in explanations. And so we had a lot of work to actually speak about the problem that we discovered. Also, the Shapley values, we can simply say that they are larger or smaller, because negative influence can be large influence. And we can do tricks like doing absolute values, but it's really hard to reason about. So we first developed a framework to talk about the behavior of asymmetric Shapley values, or Shapley values in general, which is based on the variance reduction of the target value using different sources of information. We show multiple examples where asymmetric Shapley values is probably wrong using our evaluation framework. And then we propose a solution, which is to apply generalized additive models instead of arbitrary models for modeling the problem, which I'm going to talk about. So generalized additive models are a special kind of restricted machine learning model where the target is expressed as a sum of nonlinear functions based on separate sets of features. The x1 and the xn here represent groups of features, not individual features. It's a bit weaker than the general models, but not much. And mostly the difference between the two is the part that we cannot really explain in simple terms. So we are not losing much in explanations, but we are gaining much in correctness when using generalized additive models. These can be implemented using neural networks or gradient boosted decision trees. With neural nets, we need different architectures, and with gradient boosted decision trees, we need a small modification for the training algorithm. And we show that if we only use this kind of models for predicting the performance, then we can theoretically say that the explanations will be correct in a sense. We show two theorems about this, which I'm not going to be able to actually explain here, but they mostly resolve the question of whether this can be calculated correctly. The second theorem has a condition, so it's not guaranteed to be correct in each case, but according to our measurements in practice, it almost always ends up being correct anyways. So the condition holds. And that was my presentation. Thank you. You can find me in the break if you have questions.